The purpose of this video, if you're watching, is to demonstrate how to factor binomials. In a previous video, I talked about the factoring process in general. If you remember that, if you saw that video, there's a three-step process. Number one, if you have a polynomial, we need to make sure that it's in descending order. Number two, pull out a greatest common factor if we can, if that applies. And then finally, 3 says which type of polynomial is it. It could be a binomial, a trinomial, or a 4-term polynomial for the purposes of this class. And this video will go through that first type, how to factor binomials. Because this video focuses only on binomials, don't get complacent. We know that they're all binomials, but we still need to go through step 1 and step 2 each time we do a factoring problem, even if we already have recognized what type it is. Okay, so this grid here actually kind of summarizes the different types of binomials that we can run into. It's a very common approach that's taken in a lot of algebra courses to set it up this way. I think it's a little bit misleading, however, and what I mean by that is we talk about there being 4 main types of binomials that we can consider factoring. Really what happens is there are 3 types of binomials on here that factor. The 4th type doesn't. That happens to be this first one up here. It's called the sum of squares. These other 3 will factor, and there are formulas that teach us how to do that. What's a little bit misleading is, what if you have a binomial that doesn't match any of these types at all? Well, that's actually not factorable either. And so what really happens is we start to look for patterns in binomials that fit 3 different types. What we're going to call the difference of squares, which is this type here. The sum of cubes, which is this type here, or the difference of cubes, which is right here. So if you identify that you have a binomial that fits one of these 3 patterns, it will factor according to a formula. If it doesn't fit one of those 3 patterns, then it doesn't factor. And again, that's once you have gotten to step 3 here. If you put a polynomial in descending order and then pulled out a greatest common factor, you actually did factor it. So it's that resulting piece. Once you have that resulting piece, if it's a binomial, if it will break down any further, it needs to follow one of these 3 patterns. And so I'm going to go through the process of showing you some simple examples of how to do that and what those formulas are. So again, what this sheet shows are each of the 4 types that we have categorized up here. Again, so we have sum of squares, which looks something like this, the sum of 2 things that are squared. The difference of squares, that would be the difference of 2 things that are squared. And following with that same pattern, the sum of cubes, that would be a sum of 2 terms that were cubed. And then finally, difference of cubes, the difference of 2 things that are cubed. So the names are pretty, they really indicate and follow what those formulas look like. Okay, so sum of squares. An example of that would be something like this. So I have the sum of 2 things that are squared, and if you're not sure what is squared here, a lot of times it can be helpful to break it down so it actually looks like the sum of 2 things that are squared. So what are those things? Obviously it's an x that has been squared here. That one's pretty straightforward. What this is, if you're not sure if this is a perfect square, you could actually put this number into your calculator and take the square root. If you get a whole number, that means it is a perfect square. So if I did the square root of 16 in my calculator, if I don't know what that is offhand, I would find that it is 4. So that is a perfect square. If you get a decimal, then it's not a perfect square. But 16, that is a perfect square. That happens to be a 4 that is squared. And so even though this is not factorable because it follows that one that I mentioned up here, the one that doesn't factor, it's still a useful exercise because it allows us to practice thinking about things as squares, because that same skill set we'll use down here on difference of squares. But either way, this is the sum of squares, it doesn't factor. In other words, we may say that it's prime, that it does not factor. Okay, the second one, difference of squares. Here is an example of that. And again, if we follow that same approach, an x has been squared, so I will put that x right there. And what 9 is, that's a 3 that has been squared. Again, if you did the square root of 9, you would get 3. So I could choose to write it like this. Again, this may seem a little bit over excessive, but doing something like this on a simple problem can really help you get the answers right when these terms here become a little bit more complicated. And so let's talk about the formula. If you recognize that you have a binomial that is the difference of squares, we factor that according to a very specific formula. And what that is this. Whatever is right here, this a, we're going to put this at the front of both of these terms. The b, we're going to put at the back. So simply we're going to write the a twice, the b twice inside sets of parentheses, and then one of these gets a plus and one of them gets a minus. It doesn't matter which one is which because the a and b are the same. So this is the formula for factoring difference of squares. So if I wanted to apply this formula to this problem, I can see that the x, that's the a, and 3, that represents the position of the b. So I would simply take this a and this b and I would fill them in accordingly. And again, I'm going to do another example on the next page. Let's talk about the cubes. So if you have terms that are cubed, again, we could have the sum of cubes or the difference of cubes. Again, that is a formula that we will use to do the factorization. Again, it's helpful, I think, whenever you have the polynomial to try to rewrite it as the a cubed plus b cubed. So in other words, what is a and what is b? Again, this one's pretty straightforward. It's an x that's been cubed. So I'll fill that in right here. This one, is this a cube? Again, if you're not sure, you could try to do the cube root of 8 in your calculator. If you get a whole number, that means it is. And in fact, if you did that, you would get the number 2. And some of you may have already recognized that if you took a 2 and you cubed it, you get 8. So again, similar to the one above, the x is the a, and then the 2 becomes the b. And let's do this one as well, difference of cubes. Again, it's an x that's been cubed, so let me fill that in right there. And 27, if you do the cube root of 27, you realize it is a perfect cube. That would be the cube of 3. So again, here's the a, and here's the b. So once I identify what these formulas need to look like, it becomes a simple matter of wherever we have called out in the formula the a and the b, we will fill these numbers or letters in appropriately. So what do the formulas look like? The sum of cubes and the difference of cubes formulas, some individuals find it a little bit challenging sometimes to memorize these if they have an instructor that requires them to do that versus just perhaps providing the formula. There's a little acronym called SOAP, S-O-A-P, that a coworker of mine exposed me to a while back, and I have always found that to be a very great acronym to help in the memorization of what these formulas look like for sum and difference of cubes. And so what you're going to do is notice this first set of parentheses, I've written it smaller, and the second set's a little bigger. That's because I'm going to have a binomial go in here, and I'm going to have a trinomial go in here. So what do I put there? The interesting thing for both the sum and the difference of cubes, these formulas look exactly the same as far as where you're putting the a and the b. What changes are the signs. Where do you put positive signs versus negative signs? And that's actually what the SOAP acronym helps you to remember. Okay, so this is going to be the pattern you're going to use to factor these. In this binomial, we're going to put the a and the b. In the trinomial, we're going to put an a squared at the beginning, we're going to put a b squared at the end, and we're going to put an a times a b, or just ab, in the middle. So again, this becomes your pattern. So we have an A and a B. So there's A, there's B. Now when we go to the trinomial, we square A, we square B, and then in the middle we're going to multiply them by each other. And that same pattern is used for difference of cubes as well. So again, we have the A and the B. We have A squared, B squared, and then AB. So the question is where do you put the signs, so positive versus negative signs? And that's where this acronym, again, SOAP, S-O-A-P. So let me turn this, if that makes it a little bit easier. So this SOAP acronym stands for the same, opposite, and then always positive. So same, opposite, always positive. So that indicates 3 sign choices. The first one will be the same, the second one's the opposite, and the third is always positive. So where do those signs go? Notice I have a place for 3 signs. I can put one here, the second one here, and the third one here. So I'm going to do the same sign, the opposite sign, and always positive. Well, what do you mean by the same? We're talking about the sign that is in the initial problem. So since this is a sum of cubes, that first sign is positive. So the same sign would also be positive. The next sign would be opposite, and the last would be always positive. If I follow that same acronym down here for difference of cubes, that initial sign is negative. So my first sign will be the same as that one, which is negative. The next sign will be the opposite of that, which would be positive. And the last sign is always positive. So again, it's just a neat little trick to help you memorize what these formulas need to look like. Okay, so let's actually start doing some examples. I did want to mention again here at the bottom of this sheet, if something does not follow the pattern of one of these last 3, a binomial, then it's not going to factor. So the way I like to think about it is difference of squares is going to factor. Sum of cubes will factor. Difference of cubes will factor. If it's sum of squares, it doesn't factor. And oh, by the way, there might be a whole slew of other binomials that don't fit these patterns, and they also do not factor. Okay, so let's look at some examples. And again, I want to recall what I mentioned at the beginning. We do know that these are all binomials because this is a video talking about factoring binomials. But don't get complacent. You still need to go through all of these steps. So make sure your polynomial's in descending order. Pull out a greatest common factor if you can, which actually is a factorization step, and then follow the appropriate process based on which type, and in this case we have binomials we'll be doing. Okay, so let's look at this first example. This is in descending order, so let me write those up here. So number 1, we're going to check for descending order. Number 2, we're going to do a GCF if we can, and then number 3, what type is it? And again, we know these already are going to be binomials. Okay, so descending order. This is in descending order. As you look about moving terms around to make sure you have the highest power on down, the 2 is the highest exponent. This doesn't have one, so this is a descending order. So we can check that off. Now, can we pull out a GCF? If you look at this polynomial, both of these terms have a 5 that can be factored out. You cannot factor out a letter because this term has x's, but this one doesn't. So our GCF in this problem is going to be a 5. And so I'm going to write that 5 and then determine, once I pull that out, what gets left behind. You can see that as if you divided each term by the GCF, you'll know what gets left behind. So for example, if we divide 5x squared, if we were to divide that by 5, the 5's cancel and we're left with an x squared. So that is what would show up right here. And then the second one, if I were to divide 30 by 5, that would give me a 6. And then we keep our sign. So this actually has been factored because I did pull out a GCF. Now I look at this binomial inside and try to determine if this is factorable. And because I have a plus and a square, Best case scenario, this is sum of squares, which doesn't factor, but 6 isn't even a perfect square. So the bottom line is this is one of those binomials that doesn't factor further. So I would say that if an instructor asked me to factor this, I would say that this polynomial does factor, and it looks like this because I pulled out a GCF. The remaining binomial does not factor. That doesn't break down further. So this would be my final answer for factoring this problem. Okay, so let's look at this other one. Number 1, is this in descending order? And I see my power of 2, then coefficient, so yes, this is in descending order. This problem's a little bit interesting because when you move to the second step and say, can I please pull out a GCF, a greatest common factor, you may initially think that there's nothing to do here. This has x's, this one doesn't. You have a 1 here, you know, you can't really pull out anything, but this is one of the common rules of factoring that sometimes individuals forget. And what that is once you have a polynomial in descending order, if your leading term is ever negative, which is the case on this problem, you need to pull out a negative GCF. So if you could have pulled out a different number, let's pretend there had been a 2 here, then I would have pulled out a negative 2. Because there isn't a coefficient to pull out, what you really pull out is a negative 1. And again, that is a required step. If your leading term is ever negative, you should factor out a negative GCF, even if it's only a negative 1. And so let's do that. If I'm going to pull out a negative 1, and then write my parentheses for what's left behind. When you divide this by a negative 1, you're left with a positive x squared. And when you divide the 16 by a negative 1, you're left with negative 16. So now I've pulled out my GCF and I'm ready to move to step 3, which is which type? Well, this is definitely a binomial. And if I look carefully, I may go down the path of saying, I wonder if it's difference of squares. I have a negative sign, which implies a difference. I have a square. So the question is this a perfect square? And if you want to rewrite it, you don't need to do this next step necessarily. If you're an experienced factorer, you probably would skip this. But if you're new, this might be helpful. And again, that is taking the time to write this as a squared minus b squared. So what are the two things that are squared? Well, here it's obviously the x that has been squared. Here, is this a square? And sure enough, if you take the square root of 16, excuse me, that's supposed to be a 2. The square root of 16, that is a 4. So this is the difference of squares. And this is the a, this is the b. And so we could then write our final answer. And so remember, this GCF that I pulled out, that is sitting out there. And then when you factor difference of squares, we can break it into a formula where we put the a here, the b here, and one gets plus and one gets minus, if you remember this formula that we were using. And so my a was the x, so that will go here and here. The b is the 4, that will go here and here. One gets plus, one gets minus. And so this would be the answer to that factoring problem. Okay, let's keep plugging along. This next problem, again, this is a great example of a problem where a student might get complacent and they might want to jump straight to step 3. Because if you look at this, you see a sum and you see a cube. So you're probably thinking, I wonder if this is sum of cubes. So the question is are those two terms in fact cubes? And if you look at this, I can tell that a y has been cubed. And here, an 8 is actually a 2 cubed. So a student might choose to do this, and I'm going to write this down. They might try to rethink of this as two things that have been cubed. In this case, it's a 2 and a y, okay? So if you took a 2y and you cubed that whole thing, the 2 cubed would get you the 8, and the y cubed gets you the y. And here, 64, if you actually did the cube root of 64 in a calculator, you would realize that it's a 4 that's been cubed. So a student might want to jump straight into recognizing this pattern, call this A, call this B, and then jump into the formula. And what they just did is they violated one of the first rules of factoring, which remember, descending order GCF. If you actually look at this problem, it is in descending order. I have my highest power first, but you can actually pull out a GCF. You can pull an 8 out of these two terms, and so you should do that. So if I pull that 8 out first, I have an 8, and then what's left behind on this term is going to be a y cubed. And when you take 64 and divide that by 8, you actually have an 8 that is left behind. And so when you look at this problem, now the GCF is out front, and this is the sum of cubes now. And you can realize that it is. So let me break that down. So a y has been cubed here, and that is a 2 that has actually been cubed. So this is actually the way you should break it down, where in this case, your a is actually the y, and the b is the 4. What happens is, if you fail to see this, you could break this piece down according to the formula, and then those component parts, that binomial and that trinomial possibly that you have, you are going to be left with expressions that you also could then factor further. You can pull GCFs out, and so a student would probably forget to do that, and then they're not going to get the right answer. So that's why you always pull out a GCF at the beginning, and then you will more efficiently get to the correct answer instead of possibly making a mistake later on in the problem. So let's take this sum of cubes now, and let's go write the answer. Now remember, that GCF that I pulled out, that is still sitting out front, and then when we factor a sum of cubes, we're going to have that binomial part in the beginning, and then that trinomial. And let me go ahead and above rewrite what that formula from that previous page. Let's rewrite that above so it's easier to map. So on the sum of cubes, we have the a plus the b, that's what's going to go there, and then we have a squared, b squared, a times b, negative, and plus. And so we are going to use this as our a, and this is our b, and fill them in. And so I encourage students to literally, let's just fill them in initially, and then we can worry about squaring and multiplying later. So the a and the b. So that says I have a y and a 2. Here, it's the a squared, so that's y squared. Over here, it's the b squared, so that is a 2 that I need to square. And then this middle term is a times b, so that's, y times 2. Because it is multiplication, it doesn't matter which order I do that in. So instead of writing this as y times 2, it's usually common to put the coefficient first, then the variable, because y times 2 is the same as 2 times y. So this intermediate step is great for beginners, and then on the next step you can look at, particularly at this trinomial, at these terms, and decide, is there any math I need to do? And 2 squared, that's 4. So we're actually going to write that as a 4. So the answer would be 8 times y plus 2 times y squared minus 2 times y plus 4. And again, some students may have gone straight from here to this and not needed to do this intermediate step. But when you have an A and a B that are complicated, that have maybe multiple pieces, it gets a little bit more, it's a little bit safer, more conservative to write it out this way first and then do any additional multiplication. Okay, and we'll see that probably in this problem down here. So this would be my final answer. Now this last example, I see a difference and I see some cubes. So if this factors, I'm thinking it's probably difference of cubes. Let's go ahead and follow our rules first. Let's make sure it's in descending order, and can we pull out a GCF? So descending order, when you have more than one variable, what are you supposed to do? Well, you're supposed to go alphabetically, okay? So W comes before Z in the alphabet, and so this one is fine. So look at your alphabet. But if this had actually been like an A, then technically I should have written this term first because A comes before W in the alphabet. But W comes first, and so this is correct. So it is in descending order. Can I pull out a GCF? This one has w's, this has z's. Those are not the same, so I cannot factor out a variable. And if you look at 27 and 125, there is not a common factor between those. I can't pull anything out, and so there's no GCF, and so I don't have to do it. So now we're ready to say what type. So definitely a binomial, and it's a difference. And so the question is it the difference of cubes? Well, if it is, that means then I should be able to write it as this. Two things that have been cubed. Well, clearly a w is cubed here, so that's going to be a piece of that. The question is 27 a cube? And if you do the cube root in your calculator, it is. The cube root of 27 is 3. So this just became my a. This term is what has been cubed to produce that. Same process here. We can tell that we have a z that's been cubed, and 125, if you do the cube root of 125, that actually is 5. And so it is a perfect cube, and this would be my b. Okay, so again, some students may not need to write it this way if they're an experienced factorer, but again, if you're a beginner, I would highly encourage you to do this. And then I would also encourage you to think about writing this just by filling in the a's and b's initially. And to help out here again, this will be a and b, a squared, b squared, a times b, and again, if we follow our SOAP acronym, this one was minus, so the same, opposite, always positive. Okay, so what do I need to map in here? The a, that's going to be 3w, I have a minus sign, and the b is 5z, so that's pretty straightforward, the a and the b. Here, the a squared, that means I need to take this 3w, that whole thing, and square it. And this is a common mistake that students make. They remember to square the letter, but a lot of times they forget to square the number if there's one there. So writing it this way again could be helpful. Then here in the middle, I have a, which is 3w, times the b, which is 5z. And then here I have b squared. And so the b, sorry, I wrote this a little bit tiny, the b is 5z, and I have to square that whole piece. So this is kind of an intermediate step that now we need to look at this, particularly the trinomial, and recognize that there's some computation I can do here, so I should do that. So my final answer is going to look like 3w minus 5z, and inside this trinomial, if I square 3w, squaring the 3 times 3 is 9, and then I have the w squared. Here, 3 times 5 would get me 15, and then I have a w times a z. That's the middle term there. And then here, if I square 5z, the 5 squared becomes 25, and the z squared becomes z squared. So this is what that trinomial looks like. Now I do want to point out, when you factor sum of cubes and difference of cubes, you do end up with these trinomials over here, and they do not break down. These are actually trinomials that are prime. They don't break down, and so you don't even need to attempt. If these trinomials broke down further, we would have built it into the formula. They don't, and so we don't do it that way. Okay, so this was a summary on factoring binomials. Again, it's common that we talk about 4 different types. Really, 3 of these types factor, and there are formulas to do that. This 4th type, or a binomial that wouldn't meet any of these patterns, they actually do not factor, and so we would call them prime. And hopefully that helps you and gives you some examples to follow so you can practice binomial factoring.